Abandon the session. The buses will not leave without you. And this is now my great pleasure to introduce Andrew Briggs, Professor of Nanomaterials at Oxford University. And my personal acquaintance with Andrew goes back 15 years. I spent 5 wonderful years in his lab, and it's now a great pleasure to have him here. Andrew is currently a director of the Quantum Information Processing Interdisciplinary Research Collaboration, which involved 12 universities and 4 industrial laboratories in the UK. And he's a professor fellow of St. Anne's College, emeritus fellow of Folsom College, honorary fellow of the Royal Microscopical Society, fellow of the Institute of Physics, and the libraryman of the Cloth Workers Company. He has over 500 publications, and his current research is focused on manipulating electron and nuclear spins. So today, Andrew will tell us about quantum control in carbon nanomaterials. Please, Andrew.
Well, thank you very much indeed, Ilan, and I'd like to thank Ilan Goldfarb and Noam Elias and the others for this conference and congratulate them on an absolutely brilliant conference. And thank you, Ilan, for the kind introduction, which was very accurate, unlike the speaker at an industrial conference who was introduced as having made a personal fortune of £25 million in banking in London. And when he got up, he said, I think I should just put the record straight. It wasn't in banking, it was in the electronics industry. And it wasn't in London, it was in Manchester, and it wasn't 25 million, it was 47 million. And it wasn't me, it was my brother. And he didn't make it, he lost it. I want to tell you today about quantum control in molecular nanomaterials. Unlike much of materials engineering, which is an enabling discipline, we're not here trying to develop materials to solve current applications. Rather, we're engineering materials with exceptional quantum properties that may open up a whole new range of technologies in the future. So let me start by explaining what I mean by quantum control. We use quantum mechanics in a vast range of current technologies. We use it in the whole of the electronics industry. We use it in lasers, in every CD player, and in many other areas. And of course, many of us are using quantum mechanics day by day in our materials modeling and theory. When quantum mechanics first came along, it was concerned with discrete packets of energy and discrete states, and the probability that those states would be occupied. In the 1920s, Heisenberg and Schrödinger and others developed quantum mechanics further. They explored the mathematical implications of the original theory. And Paul Dirac identified the uniqueness of quantum mechanics as lying in superposition, that a particle can be both here and there at the same time. Or if you like, a spin can be pointing both up and down simultaneously. And once you have superposition, it's then a modest mathematical step to entanglement, what Einstein called that spooky action at a distance, which in the 30s became a subject of enormous philosophical controversy, which was resolved only 40 years later by the initial experiments of people like Alan Aspect. And so what we're wanting to do in quantum control is to push these possibilities of quantum phenomena to superposition and entanglement and learn how to control them in practical materials. What will this offer if we succeed? It'll offer quantum computing, the application of quantum computing that has released literally hundreds of millions of dollars, particularly in the US, is code breaking. That once a large-scale quantum computer is made, almost all current public key cryptography will become unsafe, and it will become unsafe retrospectively. And therefore, if you can make a big quantum computer, you can sell it to the Americans for almost any figure you name, and you could sell it for an even larger figure, provided you promise not to sell one to anybody else. And even before we have the large code-breaking machines, quantum computers will be useful for simulating materials, partly through simulating the evolution of a time-dependent Schrödinger equation, but also algorithms are now coming along, for example, quantum metropolis Monte Carlo algorithms that will find whole new applications in materials modeling once quantum computers can be built. And it's now becoming clear that there'll be earlier applications, for example, in quantum-enhanced metrology and sensing. Which materials are suitable for this? We don't know. But some of the materials in which quantum control is already rather well established include conventional superconductors, particularly aluminium because of the stable oxide for making Josephson junctions, a wide range of semiconductors, the compound semiconductors based on the gallium arsenide family, silicon, particularly phosphorus dopants in silicon, and what I'm going to tell you about this evening, carbon materials. And I've illustrated a couple of them there. I'm going to tell you a bit about how you can do quantum control in atoms that you can insert inside molecules consisting of 60 or more carbon atoms, the so-called endohedral fullerene family. And then I'll show how we can put those inside carbon nanotubes to make extended structures. So the outline of what I'm going to talk about today is to tell you about the structures and materials, to show how we can use combinations of nuclear and electron spins to make quantum memories, to show you a whole new way of putting information into molecular materials in collective spin states, and finally to show you the start that's been made on using entanglement amplified phase for sensors. And in particular in these materials, we'll be looking at the spins, the electron spins, and the nuclear spins. And I'm going to introduce a way of thinking about these superposition states that are crucial to the whole of quantum control. Imagine a globe of the Earth. I'll come over here and show it. So imagine you've got a globe. Can you still hear me, or has the sound pegged out? The sound's pegged out. All right, I shall become a pop star. Imagine that you've got a globe of the Earth. And you have the North Pole up here and the South Pole down there. And the North Pole represents spin pointing upwards in a magnetic field, and the South Pole represents spin pointing downwards in a magnetic field. And it's easiest to work in a frame that's rotating at the Larmor frequency of your electron spin in that field. Now, classically, the spin could be pointing up or it could be pointing down, one or the other. In our quantum world, the spin can be both up and down simultaneously, but the way to think about that is not to think of it as being somewhere along the axis of the globe, but rather think of it as being on the surface of the globe. So the state has both latitude, telling you how far north and south it is, and longitude, telling you how far east and west. And part of the magic of quantum control is using both the latitude and the longitude. The longitude corresponds to what in technical quantum terms is the quantum phase. And a very important thing in any kind of quantum technologies is how long the spin remembers where it should be on the globe. So if you imagine you've got an equal amount of north and south pole, then you're on the equator, but Nairobi is not the same as Singapore. And the time for which a spin remembers what its latitude should be in the trade is called T1. So that's how long it remembers whether it's north or south. And the time for which it remembers east or west is T2. And that'll become important as we go along. Here is a sketch of a vision that I had a few years ago now for the kinds of ways that one might build a quantum computer using molecular materials. So what you've got is a carbon nanotube containing some spins and with some electrodes on it. Whether or not a quantum computer will ever be built that way remains to be seen. But what is undoubtedly a matter of historical fact is that this vision has inspired an enormous amount of work studying the relevant materials to see what their quantum properties are, how well they can be controlled, and how useful they might be. So let's start with the kind of way that one can make devices of nanotubes containing spin-bearing materials. This is a picture from the laboratory of Mark Butelar in Cambridge, who works with us, and it shows a single-walled carbon nanotube, which you can just about see in this SEM image, with electrodes, and the important bit is that here the electrodes are forming two quantum dots. And samples like this were used to demonstrate a phenomenon called spin blockade in these carbon nanomaterials. And the next slide shows you some of the results. These diagrams take quite a long time to get your head round if you're not used to them, so I won't talk you through it, except to say this, that a signature that you've got spin blockade happening is that you get negative differential resistance. So that means you've gone negative on this color scale here, in other words, blue. And in these diagrams, you can see the blue regions there demonstrate that we've got spin blockade in the transport of current through the device. I'll gladly tell anyone over dinner tonight more about these experiments, but the key point is that they demonstrate that we're able to make electrical measurements where the current depends on the behavior of individual electron spins in the device. Or to be a bit more technical, you've got pairs of spins, and whether or not a current flows depends on whether that pair of spins forms a singlet or a triplet state. Well, now, the material on which this experiment was done was a so-called Peapod structure. They're called Peapods because of how they look in the electron microscope. And we've made quite a lot of these now, and quite a lot of different ones. This particular picture here is a TEM picture of a Peapod where you've got a nanotube, diameter about 1.4 nanometers, containing cages of 82 carbon atoms, each of which contains one cerium atom. And not so long ago, we were quite proud of the quality of this picture and the clarity with which you could see the individual cerium atom in each fullerene cage. But times have moved on. We'll have a plenary lecture tomorrow about aberration-corrected electron microscopy. And this is the kind of picture that is now routine of these materials. So this is taken at 80 kilovolts in an aberration-corrected Titan machine. I'll show you in a moment what the spatial resolution is. But this is a movie taken with a time resolution of 80 milliseconds. So it's over 12 frames per second that are being taken. If you turn the current down, the beam current down, then everything remains static and you can watch these carbon materials for almost as long as you like. Because at 80 kilovolts, you've almost eliminated the knock-on damage from the electron beam. But by turning the current up, Jamie Warner, who took this picture, was able to make these nice movies where you can see things moving around under the influence of the electron beam. And in particular, here is a fullerene molecule that has formed inside the carbon nanotube under the heating effect of the electron beam. This is the kind of resolution that you're getting in these pictures. The length of an sp2 carbon bond is 133 picometers, and you can see that the carbon-carbon bond is being readily resolved. And here in this cartoon, you can see the structure of the carbon atoms in the wall of the carbon nanotube and how you're able to image this kind of structure with atomic resolution of the carbon atoms. A key parameter or pair of parameters in single-walled carbon nanotubes is their pair of chiral indices, the MN indices, which tell you how the nanotube is rolled up and determine not only the diameter of the nanotube, but also its electronic properties. And by analyzing the diffraction data, you can readily see you can determine the MN indices of the nanotube. And there's one further point that I'd like to make before I move on, and it's this, that one of the developments that's happening in this field is the ability to make samples for the cryogenic transport experiments that are suitable for imaging directly by aberration-corrected, low-voltage, high-resolution transmission electron microscopy. And that means that you can, on the nanoscale, determine the functional properties of the materials and then look in the electron microscope with atomic resolution at precisely the bit of stuff that you were measuring in your experiment. As nanotechnology gets smaller and smaller, so the position of a few atoms changing can alter the properties of your device. And this will enable you to image the device and relate its detailed atomic structure to the particular properties that you measure. Well, now, as nanotechnology makes its inexorable progress and we get structures that are smaller and smaller, so there's a growing range of quantum states over which there's the possibility of having control at the level of the individual quantum states. Within the molecular materials, the fullerenes are a very versatile family, and probably the most miraculous fullerene molecule of all consists of a cage of 60 carbon atoms, inside which we can place one nitrogen atom. And rather remarkably, the nitrogen atom does not bond chemically with the carbon, and it's a miracle because the nitrogen is almost the most reactive atom you can think of, but it just sits in the cage, enabling you to do, as it were, atomic physics in a condensed matter structure. Here's a little movie. Here's a little movie of how we make this nitrogen in C60. So I hope this doesn't make you seasick, but after a bit it'll settle down. And underneath there is a furnace from which we sublimate fullerene molecules, C60 cages. And then to one side there's an ion gun where we ionize the nitrogen, so we're firing individual nitrogen ions at the fullerene cages. And then there's a plate like this, which is cooled to room temperature or water temperature, on which they can condense. Now, when you fire the nitrogen ions at the C60 cages, chances are either you'll miss or there'll be a big splat and the thing will just be blasted to bits. But just occasionally, a nitrogen ion hits the cage and the whole thing stays intact, and you're left with this nitrogen atom inside the C60 cage. We call this nitrogen at C60 in the slang, and it has quite remarkable quantum properties. Let me show you some. These are electron paramagnetic resonance data showing you the values of T1 and T2 for the electron spins in these N at C60 molecules as a function of temperature. And remember, T1 is how long it remembers how far north or south it should be, and T2 is how long it remembers how far east and west it should be. And one of the reasons why T2 is usually more delicate than T1 is because changes in the east-west don't involve any change in energy, whereas changes in north-south you have to emit or absorb phonons or some such process. So here we are for our nitrogen at C60, and as you go down in temperature, you can see that the T1 time becomes more than a second. And that number will become important for something I'm going to tell you later on. For the T2, well, it turns out that there are various different transitions in the electron paramagnetic spectrum. Some of the transitions, as you cool it down, T2 gets shorter, but then it gets longer. And for others of the transitions, as you cool it down, it gets shorter, and then it just becomes disastrously short. And the benchmark figure to have in your mind when you look at the numbers there is that the time to manipulate an electron spin is measured in tens of nanoseconds. And you can see that the T2s that we're getting there go up to about 1/4 of a millisecond. So that's allowing you to do something like 10,000 manipulations before the electron spin forgets whether it should be east or west. But we can make the memory times even longer. You can imagine if you're trying to build a quantum computer or other technologies, you want to remember the information for as long as possible. And the way to store the information for even longer is to store it in the nuclear spin, because the nuclear spin has much weaker interactions with the environment, although the electron spin is much better for control and for initialization and for coupling to other spins. So here's the sort of picture. We might have a superposition state of this electron spin level and this electron spin level in a magnetic field with some hyperfine splitting to slightly different energies because the nuclear spin can be pointing, that's the red arrow, either down or up. And we can apply microwave and radio frequency pulses to give you any of the 4 transitions indicated by blue dotted lines there. So the way that one does an experiment like this is as follows. First, you start in this state here, so that's electron spin down, nuclear spin down. And then we apply a pulse, a microwave pulse, that will give us a superposition of the electron spin being down and being up. Because of the way you do these, you represent it on the block sphere, that's often called a pi/2 pulse. And then we might want to transfer this state to that nuclear spin state, and we do that by applying a radio frequency pulse that will take us from there to there. And now, because we're changing the nuclear spin from there to there, we call that a pi pulse because it's a rotation of pi. And then finally, we'll move the electron spin that's down there up to here, and we do that with a pi microwave pulse. And now we've got the information in this superposition state, and that's a nuclear spin superposition state. Don't worry if you haven't followed every detail of that, but we can do this process in the nitrogen at C60 molecules, and here's the kind of result. You see, here, the blue curve tells us what happens if we just try to store the information in the electron spin state. And we're measuring the echo intensity in an experiment that's deliberately designed to tell us how long the electron spin is remembering how far east or west it is. And it can measure it for, well, it's falling to 1/e in a time of 150 microseconds or so. Now, the red curve here is telling us how well we do if we take the information that's in the electron spin state, move it to the nuclear spin state, leave it there for a while, and then bring it back to the electron spin state. So this is forming a sort of memory element for our quantum computer. You can think of it as a hard disk for the quantum computer, if you like. And now this is a different time scale here. And in this particular experiment, the lifetime, well, the information fell to 1 over E in a time of 54 milliseconds. So we're already getting something approaching a couple of orders of magnitude increase in memory time. And probably we can do much better than that. And I'll show you why in the next slide. But the key point to make here is that the limitation is probably a materials limitation. So if one's going to improve these technologies, the way to do it is going to be not just through doing cleverer physics, though that has a part to play, but it's going to be by getting better at the materials for these quantum technologies, for quantum control. And in this particular case, it's a question of the purity of the nitrogen at C60. So now, here is some data on a different material system. These are phosphorus dopants in silicon. And the point that I wanted to show you from this slide is as follows. This curve here, with the squares as the data points, is a measure of the T1 time for the electron spin of a phosphorus dopant in silicon. And these red curves here are from two different experiments, this one with a rather cleverer magnetic resonance pulse sequence, for the total memory time if you use the nuclear spin, transfer it to the nuclear spin, and then transfer it back to the electron spin again. And this is a more severe test because this is T2, whereas the squares here were only T1, which is usually easier. And the fundamental limit on how long you can remember for in this system is that T2 of the nuclear spins is limited by twice the value of T1 of the electron spin, shown by this broken curve here. And you can see how at least at higher temperature, it got worse at lower temperature, but at least here, that theoretical limit is being approached. So now you can ask yourself, well, how good are we going to be able to make our nitrogen at C60 quantum memories? And, well, I won't embarrass anybody by asking if you can remember back. Well, maybe somebody can remember back. What was the T1 that we could achieve with nitrogen at C60? Who can remember? Pardon? No, it was more than milliseconds. It got up above 10 to the naught on the second scale. So the T1 for the electron spins can be more than a second. So if we can get the materials science right, there's no reason why our quantum memories using the nuclear spin should not also exceed a second. Remember, the manipulation time for the electron spins is tens of nanoseconds. So we may be in with a chance of doing millions of operations within the useful time of our memory. Let me now move on to a totally different topic. Oh, that just shows you that in this particular experiment, 1.75 seconds was achieved. And I think now it's gone up to 2 seconds. That's for a different material system. So let me now move on to another topic, which is how we may be able to store information in electron spin states. And the vision here is to have a quantum computer where we've got a superconducting coplanar microwave strip line. We've got a Josephson junction device here, which gives us nonlinear operations. And we're going to store the information in the collective states of spins, which could be some of our nitrogen C60 molecules, that we insert into this cavity resonator. And if you want to get some idea of the dimensions, this might be about 5 microns, and that might be 10 millimeters or something like that. Now, one of the fathers of computing, as we now know it, is Alan Turing. You may know that the Turing machine is the prototype of any machine that you're going to use for doing computing. And this is a cartoon adapted by Dave Schuster of how this kind of computer is really like a quantum Turing machine. So you need a processor head, and that is this transmon device here. You need, so that's the equivalent in the cartoon. You need a memory interface between the processor and the memory, and that's this cavity. You need a homogeneous storage medium. In the Turing machine, that's this paper tape, and in our case, it's the electron spin ensemble. And then you need a way of winding the tape. So you've got to be able to move backwards and forwards. Now, how it works in the collective spin states is as follows. We use our Josephson junction device, the transmon in that picture, to create a single microwave photon in the cavity. And that's established technology. That can be done. The photon is absorbed by the electron spins in our array of molecules as a collective spin state. So you can think of it as being a little bit in each one, or if you can get your head around the quantum mechanics, it's a superposition of the excitation being in the first molecule plus the excitation being in the second molecule plus the excitation being in the third molecule, and so on, all divided by the square root of n, where n is the number of spins. If you just left it there, it would superradiate back into the cavity. But we don't do that. We apply a magnetic field gradient. And the effect of the magnetic field gradient is to introduce a phase change in the quantum superposition, varying spatially across the ensemble. Then we take the field gradient off. And we've now put a phase gradient across the ensemble, which can be described by a k-vector. Now we put another microwave photon in, apply another gradient, turn the gradient off, and we've got that next bit of information with a different k-vector. Another bit of information, another field gradient, turn the field gradient off, and so we go on putting them in. And then, when you're ready to take the information out, you apply the reverse field gradient, and you want the integral of the gradient times time to correspond to the particular bit of information that you want to get out, and then you take the gradient off. And that way you unwind it and get out the piece that you wanted. Now I can show you a little movie made by G.I. Taylor, which illustrates this in fluid dynamics. And the way that G.I. Taylor got this to work in fluid dynamics was to take some very, very dense concentrated sugar solution with a viscosity about 1,000 times the viscosity of water, but it still acts as a Newtonian fluid. And then with this little tube, he introduced a spot of ink. And that's G.I. Taylor's finger winding it round. And you see, as you wind this round, you introduce a whole lot of shear into the fluid, and the little blob of ink gets dispersed throughout the fluid. But the remarkable thing is that it's reversible, so that when you unwind the fluid, that ink that was dispersed throughout it will come back to a single blob. And there it is. Isn't that lovely? Now, I think it deserves some applause, even though he made that movie about 40 years ago. Now, that's what we're doing with the information in our collective spin states. Now, how do I get this back? Wait a minute. I can do it. I think. There we go. That's what we're doing with our information in our collective spin states. When we apply the field, it goes into this mode with a k-vector. The phases all cancel each other out. It can't couple to the cavity. We reverse the field, and it can couple to the cavity again. And people often use the metaphor of a hologram. So it's rather like this, that in a conventional photograph, one point on the object is represented by one point in the image. In a hologram, each point in the object is represented in the whole hologram by the phase relationships across it. So whereas conventional quantum computing thinks of one bit of information mapped into, in our case, one molecule, now we're mapping the information into 1 billion molecules and encoding it in the phase. and it works. So here is an experiment where we put 2 pulses in. The first one was positive, the second one was negative. And you can read the information out, and you can either read it out in the same order that you put it in. So here we're reading it out. So there's the positive one, and there's the negative one. So that's first in, first out. But you say, well, I want this to be a random access memory. I'd like to be able to do last in, first out. And there it is. So pass minus, and you take out the second one first and the first one second. And here's a different way of encoding the information in the bottom curves, but the same is true. You can have first in, first out, or you can have last in. Whoops. This pointer's not working. Yes, it is. You can have last in, first out. So that's it working for 2 bits of information. It will even work for larger numbers of bits of information. And, whoops. Sorry, I just lost my pointer. Here's where we tried it. Whoops. We tried to see how many we could put in, and Hua Wu, who did the experiments, has here put in 100 bits of information, and they're randomly plus or minus, minus or plus, and here she is reading them out. In this case, she did last in, first out. So you see that spike there has come out there, and these ones here have come out here. And if you're interested, you can even look at the enlarged thing here and show that if you start here, first in, last in, here, last out, first out. And then finally, we wanted to see if we could use this trick of putting the information into the nuclear spin states and then reading it out sometime later. And there is a byte put into the electron spins, transferred to the nuclear spins, left there, then transferred from the nuclear spins to the electron spins and read out again. So this method of encoding the information in the collective spin states is now rather nicely demonstrated, at least for the particular case that I was showing there. The last topic I wanted to tell you about is entanglement enhanced field sensing. And again, it takes a little while to get your head around the figures, so let me just tell you the results. This is a molecule of trimethyl phosphate, and it's got 9 equivalent nuclear spins around a phosphorus atom. And when you do an NMR experiment, in the rotating frame that I was telling you about for my globe of the Earth, what's technically called a block sphere, if you don't change the magnetic field, and if you're working nicely within T2, then when you take something down to, say, Nairobi, it'll stay there. If you change the magnetic field, then it will gradually process, either to Ecuador or to Singapore, depending on the change in the sign of the magnetic field. If you entangle a number of spins, then the rate at which the spin processes around the equator is multiplied by the number of spins that you've entangled. And that gives you the opportunity for entanglement-enhanced sensing of magnetic fields, with applications as diverse as prospecting for oil or finding submarines under the surface, or, of course, nanomagnetic field sensing. In this particular case, we had 9 spins entangled, and the point that this complicated diagram is showing you is that where you've got 9 of them entangled, you're getting 9 times as fast a precession frequency as you do for the unentangled spins. And in fact, Stephanie Simons, who's working on this, has now got it to work with 12 spins. There it is working with 12 spins, and she's now working on an experiment with 27 spins. I must draw to a close. This is a summary of some of the points that I've tried to cover, and the way that I've tried to share with you the excitement that we can engineer these materials with exceptional quantum states, and then do the quantum control in these materials that will open the way, I believe, to a whole family of new technologies that exploit the full resources that quantum mechanics offers us.
Thank you very much. Thank you very much, Andrew, for this very interesting talk. And questions, please.
If I go back to something that you said in the beginning about putting nitrogen inside of C60 and then condensing it on a plate, how do you separate out the ones, the very few that actually have a nitrogen in the inside from all of the rest of them that simply survived and nothing happened?
Well, you're absolutely right. The property that makes these molecules fantastic for quantum control makes them amazingly difficult to purify. It's namely that the nitrogen scarcely interacts with the carbon cage at all. And therefore, the C60 cages that have a nitrogen inside are chemically almost indistinguishable from the empty C60 cages. Now, add to that difficulty the fact that we don't have a very high hit rate. So the C60 cages that we scrape off the plate, I mean, you know what this subject has done, don't you? What we scrape off is soot. And this subject has made soot academically respectable. It's marvelous. When we scrape off the soot, we remove all the junk, the amorphous carbon. We're then left with our C60 molecules. About 1 in 10,000 has a nitrogen atom inside, and the ones with nitrogen are almost indistinguishable. And what we actually use is high-performance liquid chromatography, recycling. And through a very laborious but actually effective process of going round and round and round, you eventually separate out in the liquid chromatography this much smaller peak, which has in it the nitrogen with C60. And in fact, although it's laborious, it's so effective that we can get the stuff up to as high a concentration as we need. It's just how long you want to carry on running the recycling HPLC.
More questions? Well, then maybe I have a question. So what would be the recipe for picking up a different system rather than C60 and the nitrogen? What would be the algorithm?
Oh, how would you choose it? You start off by looking at these vital statistics of the T1 and the T2 of the quantum states that you're thinking of controlling. So it could be charge moving around, it could be superconducting currents, it could be excitons. There's actually a wide range of possibilities. In the diamond, people use the nitrogen vacancy defect centers. But I don't think a systematic search has been done. The nitrogen at C60 is the best molecular system that's ever been found, but we're now finding others like yttrium at C82, which are almost as good. And I think it's an open question, and the search is on. And, who knows? We may find better systems than the ones that we're using at the moment.
Excellent answer. You all heard. The glove has been thrown. If anybody wants to pick it up. Question? Please. Shmuel.
I beg your pardon?
The highest temperature used in your experiment was about 9 Kelvin. It's quite a major obstacle for normal use.
Yeah. So I think there are two parts of the answer to that question. One is that some of the data that I showed you, for example, those data there were taken at room temperature. So you can get these things to work very well at room temperature. As people work on the materials science of the nitrogen vacancy centers in diamond, they're finding that those are almost as good at room temperature as they are at cryogenic temperatures. So I don't think there's any impossibility at all about working it at room temperature. The only thing that I would say is that some of these experiments are so hard and so difficult that actually the cryogenics is the easiest bit of the temperature. And therefore, if you can make your life a little bit easier with a bit of liquid helium, you're glad to do it.
All right. I think we should thank both our exceptional speakers of this session.